Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
You know, there is this incredible high-stakes premise at the heart of the movie Project Hail Mary.
Oh, yeah.
If you haven't seen it or, read the book by Andy Weir that it's based on, the setup is just both terrifying and utterly captivating.
It really is.
You have this solitary human astronaut, played by Ryan Gosling in the upcoming film, who wakes up from a coma millions of miles from home.
Right, with total amnesia.
Exactly. He's suffering from amnesia, but slowly, the horrifying reality of his situation just sort of trickles back in. Earth is dying.
Yeah, not a great situation to wake up to.
No, not at all. Our sun has been infected by this spacefaring, energy-eating microorganism called astrophage, which is essentially dimming our star and plunging humanity into an ice age.
Which is such a brilliant sci-fi concept.
It is. And Gosling's character is on this desperate one-way Hail Mary mission to another star system, one that mysteriously seems resistant to this astrophage infection.
Alceti, I think it was.
Yeah, Alceti. He has to go there to figure out why it's resistant and hopefully bring a cure back to save Earth.
And without giving away too much, he encounters a completely alien life form.
Right, an engineer he names Rocky. And they have to work together dealing with fictional alien microbes and alien physics. It's pure, thrilling science fiction.
Absolutely.
But here is the reality that we are unpacking today, and it fundamentally alters how you and I should look up at the night sky.
It really does change everything.
We no longer have to treat that core premise, the idea of pinpointing an exact, specific star system to travel to in order to find alien life, as just fiction.
No, it's not just a guessing game anymore.
Exactly. We don't have to guess where a real-life astronaut should point their spaceship. The astronomical community has literally just mapped out the exact coordinates.
It is a profound shift in how humanity is approaching the cosmos. I mean, for decades, discovering exoplanets, planets orbiting stars outside our own solar system, was basically an exercise in bulk collection.
Just grabbing whatever we could see.
Exactly. And through incredibly hard work, we have confirmed the existence of more than 6,000 of them.
6,000 completely alien worlds. That's just wild to think about.
It is. But for a long time, looking for life among them was a numbers game, with odds that were, frankly, astronomically stacked against us.
A needle in a haystack of planetary proportions.
Right. But what we are looking at today is the result of a brilliant international team of scientists who took that massive, overwhelming catalog of 6,000 planets and ruthlessly, mathematically filtered it down.
They cut out all the noise.
They really did. They have pinpointed exactly 45 rocky worlds.
45 out of 6,000.
Just 45. And these specific worlds represent our absolute best physical and chemical bets for being habitable. We have a definitive, rigorously vetted shortlist for the search for extraterrestrial life.
And the mission for our conversation today is to figure out exactly how scientists pulled that off.
It's quite the detective story.
It really is. We are going to explore the rigorous criteria that reduced 6,000 planets down to just 45, and then an even stricter gold standard list of 24.
The best of the best.
Yeah. We are going to look at the bizarre alien biology that might exist under different colored suns, the extreme planets living on the razor's edge of survival, and the monumental next-generation telescopes that are actively using this map right now.
There's a lot to cover.
There is. But before we get to the telescopes, I want to challenge the premise itself.
Okay, let's hear it.
When we say habitable, we usually mean the habitable zone or, the Goldilocks zone. Not too hot, not too cold. Liquid water can exist on the surface.
Right, that's the classic definition.
But isn't this entire concept incredibly Earth-centric? Like, we're assuming alien life needs exactly what we need.
That is a very common and very valid critique. It's often called water chauvinism or carbon chauvinism in astrobiology circles.
Water chauvinism, I like that term.
Yeah, it's this idea of why assume life needs water? Why couldn't it use, say, liquid methane, like we see in the lakes of Saturn's moon, Titan?
Right, because Titan is covered in liquid, it's just not water.
Exactly. The answer, though, comes down to the brutal efficiency of thermodynamics and chemistry. Water is the universal solvent.
It just works better than anything else.
It really does. It has a unique molecular structure. It's polar, meaning it has a slight positive charge on one end and a slight negative charge on the other.
Which makes it act kind of like a magnet.
Kind of, yeah. This allows it to dissolve a massive variety of substances, facilitating the incredibly complex, rapid chemical reactions required to build proteins, form cell membranes, and essentially allow biology to happen.
So it's just the best medium for mixing things up.
Right. Liquid methane, on the other hand, is simply too cold. Chemical reactions in liquid methane happen at a glacial pace.
So even if there were microbes in those methane lakes on Titan?
If life exists there, its metabolism would be so incredibly slow, we might not even recognize it as alive.
Wow. So it's not just a lack of imagination on our part. It's that water is objectively the best chemical arena for complex life to evolve in a reasonable time frame.
Exactly. And liquid water has a very strict temperature range dictated by atmospheric pressure.
Right, because if a planet is too close to its star,
the water boils away into steam, creating a runaway greenhouse effect.
and if it's too far out, the water just freezes solid into ice.
Locking away any potential for active biochemistry, the habitable zone is simply the physical geometry around a star where that liquid phase is actually possible.
Makes sense.
But what makes this new catalog of 45 planets so revolutionary is that researchers aren't just using a simple flat calculation for distance anymore.
Right, because the stars themselves are completely different from each other.
Exactly. They aren't all just copies of our sun.
I was actually thinking about this earlier. When you go camping, if someone builds a massive, roaring, 10-foot-tall bonfire...
Oh, yeah, you can't get anywhere near that.
No, you cannot sit 3 feet away from it. You have to take your folding chair and sit way, way back at the edge of the clearing just to feel comfortable. But if the fire dies down and it's just a tiny little pile of glowing red embers, sitting back in the clearing leaves you freezing. You have to huddle right up close, practically putting your boots in the ash.
It's a great analogy.
The perfect spot physically changes depending on the size of the fire.
That is absolutely true for size, but to truly understand planetary habitability, we need to push that analogy just a little further.
Okay, how so?
Imagine that instead of just radiating different amounts of heat, the campfire is burning a chemical that specifically targets the fabric of your jacket.
Wait, what? That's terrifying.
Right. But hear me out, because stars are not just different sizes. They emit entirely different spectrums of electromagnetic radiation.
Ah, right. The color of the light.
Yes. You have massive, hyperluminous blue giants that burn incredibly hot and pump out massive amounts of ultraviolet radiation.
Which would instantly fry anything on the surface.
Exactly. And on the other end of the spectrum, you have red dwarfs. These are small, dim, and relatively cool, emitting mostly infrared light.
And infrared light interacts with an atmosphere entirely differently than the visible yellow light from our sun, doesn't it?
Fundamentally differently. This is a critical nuance that actually shifts the physical boundaries of habitability.
Because of greenhouse gases.
Yes, precisely. Water vapor and carbon dioxide, the primary greenhouse gases, absorb infrared radiation far more aggressively than they absorb visible light.
Okay, so with our sun
emits a lot of visible light, which mostly passes right through our atmosphere, hits the surface, warms it up, and then the Earth radiates that heat back as infrared.
And then some of that outgoing infrared gets trapped by the greenhouse gases.
Exactly. But if a planet is orbiting a red dwarf, the star is already blasting the planet with mostly infrared light right out of the gate.
So the atmosphere acts like a sponge that is perfectly tuned to soak up that specific type of incoming light.
Precisely. This means the atmosphere traps heat much more efficiently from the star itself, not just from the surface bouncing it back.
Wow, so what does that mean for the habitable zone?
Consequently, if you are orbiting a red dwarf, the inner edge of the habitable zone, the point where things get too hot and oceans boil away, gets pushed further out from the star than you might calculate based on raw temperature alone.
Because the atmosphere is holding on to so much more of that specific heat.
Right. The specific color of the host star actually changes the physical geometry of where a planet can safely survive. It's an incredibly complex thermodynamic puzzle.
Which leads to some just staggering visual implications for what life on these 45 catalog planets might actually look like.
Oh, the biological possibilities are amazing.
Because if the light hitting the planet is fundamentally different than the light hitting Earth, any biology that evolves there is going to adapt to that specific stellar spectrum.
It has to survive.
We are conditioned by sci-fi movies to expect alien planets to be covered in lush green jungles.
The classic Star Trek aesthetic.
Exactly. But the only reason plants on Earth are green is because chlorophyll absorbs the abundant blue and red wavelengths from our sun and reflects the green light back at our eyes.
Right. It is a highly specific evolutionary adaptation to the spectral output of a G-type main sequence star, our yellow sun.
So let's play this out. Imagine one of these 45 planets is orbiting a star that is slightly hotter and more intense than our sun, pumping out high-energy ultraviolet radiation.
Okay, a much harsher environment.
Yeah. Researchers have theorized that surface organisms couldn't just absorb that UV bombardment without suffering massive cellular damage. They would fry.
DNA gets shredded by UV.
Right. So what do? They might evolve biofluorescence.
Oh, that's fascinating.
They could absorb that deadly invisible UV light and re-emit it as lower energy, safe, visible light.
To protect themselves.
Yeah. You could have a scenario where an entire alien forest, the trees, the ground cover, the wildlife, is literally glowing in neon blues, greens, and pinks under the intense glare of their sun just to survive.
It is a breathtaking biological solution to a stellar physics problem.
It paints such an incredible picture.
Yeah.
But what about the other end of the spectrum?
The inverse is equally fascinating. Consider a theoretical plant on a planet orbiting a red dwarf star.
Okay, so mostly infrared light.
Right. The star is emitting primarily dim red and infrared light. There is very little high-energy visible light available.
So they can't afford to waste any of it.
Exactly. If an organism on that planet wants to perform photosynthesis and survive, it cannot afford the luxury of reflecting any visible light away. It needs every single photon of energy it can capture.
So it wouldn't reflect green. It might just absorb everything.
Yes. The foliage on a world orbiting a red dwarf could appear completely pitch black to human eyes.
Pitch black jungles. That's incredible.
Or, depending on the specific pigments it evolves, perhaps a deep dark purple or a rusty reddish brown.
It's wild to think about. The very colors of the ecosystem are dictated by the star in the sky.
They absolutely are. When we look at this curated list of 45 planets, we are really looking at 45 potential canvases where evolution had to solve the problem of survival using an entirely different palette of light.
Okay, so we know the recipe. We know the constraints of the habitable zone, the thermodynamic requirements for liquid water, and how the color of a star fundamentally alters planetary chemistry.
We have the baseline.
Right. So let's move from the theory to the actual VIPs of this new cosmic catalog. Let's look at the actual data.
The detective work required to build this list is just astonishing.
I can imagine. How'd they actually do it?
Well, it was heavily driven by researchers working alongside an international team of undergraduate and graduate students. They had to synthesize mountains of data.
Because there's so much out there now.
Yes. Specifically, they cross-referenced massive exoplanet archives with high-precision astrometry data from space observatories like Gaia.
Now, Gaia is the one that's been mapping the exact positions of stars, right?
Exactly. It's been meticulously measuring the positions, distances, and motions of over 1 billion stars.
1 billion.
Yeah, it's mind-boggling. And by combining the known exoplanets with hyper-accurate measurements of their host stars, they could recalculate exactly how much radiation these planets are actually receiving.
And out of the 6,000 confirmed exoplanets, they found exactly 45 rocky worlds that fit the criteria.
The Elite 45.
But what really caught my attention is that they went a step further and created a subset within the subset.
Ah, yes, the 24.
Out of those 45, they identified 24 planets that reside in what they call a narrower 3D habitable zone. How does a 3D model change the game? What were we doing before, just drawing 2D circles around stars on a chalkboard?
In a way, yes, we kind of were. Early habitability models were largely one-dimensional or two-dimensional.
Just based on distance.
Exactly. They looked at the energy coming from the star, the distance of the planet, and assumed a uniform temperature across the entire planet's surface.
Which is obviously not how planets work. I mean, look at Earth. The equator is vastly different from the poles.
Precisely. Planets are not uniform spheres of rock. They are dynamic three-dimensional systems. So the 3D models incorporate global circulation models, or GCMs.
Okay, what are those?
They are very similar to the supercomputer models we use to predict climate change and weather patterns here on Earth.
Oh, wow. So they are essentially modeling alien weather.
That's exactly what they're doing. They're factoring in atmospheric circulation.
Like wind and ocean currents.
Yes. How does heat physically move from the equator of the planet, where it receives the most direct starlight, to the poles?
It makes a huge difference.
It does. And does the planet have a thick cloud cover? Clouds are highly reflective. A thick cloud deck on the day side of a planet can bounce a significant portion of the star's energy back into space.
Which would naturally cool a planet down.
Exactly. This is known as the planetary albedo. And perhaps the most critical factor these 3D models address is planetary rotation, specifically something called tidal locking.
Right, because a lot of these planets on the list orbit red dwarfs. And to be in the habitable zone of a dim red dwarf, you have to be huddled incredibly close to the star.
Much closer than Mercury is to our sun, in many cases.
And when you are that close to a star, the immense gravitational pull actually acts as a brake on the planet's rotation, right?
Yes, over millions of years, the planet's rotation slows down until it perfectly matches its orbital period. The result is tidal locking.
So one side of the planet permanently faces the star in perpetual blazing daylight, while the other side is cast in endless freezing night.
Just like how our moon is tidally locked to Earth, we only ever see one side.
Right. So if you just use a basic 2D model, you might average the temperature and say, oh, the average is 60 degrees Fahrenheit, it's habitable.
But in reality, the day side is boiling rock and the night side is a solid sheet of nitrogen ice.
Exactly. That average doesn't exist anywhere on the surface.
This is where the 3D global circulation models are essential. They allow scientists to simulate whether an atmosphere has enough density and wind speed to carry heat from that blazing day side over the terminator line, the twilight zone, and onto the freezing night side.
Basically, can the winds move fast enough to keep the dark side from freezing completely?
Yes, preventing the atmosphere from literally freezing and collapsing out of the sky onto the dark hemisphere.
That's wild. So the 24 planets on the final gold standard list are the ones where these rigorous, conservative 3D climate models confirm that liquid water could sustainably persist under those crazy complex atmospheric dynamics.
Exactly. They survive the toughest simulated conditions we can throw at them.
Let's actually talk about some of these specific planets.
Sure.
If you follow space news at all, you've probably heard of a few of these. You have Proxima Centauri b, which is our literal next-door neighbor, practically in our cosmic backyard.
Just over 4 light years away.
Right. Then you have Kepler 186, which made huge headlines years ago as the first Earth-sized planet found in a habitable zone.
A very famous system.
But the system that seems to have the astronomical community completely fixated is TRAPPIST-1.
Oh, TRAPPIST-1 is the holy grail right now.
Specifically, the planets TRAPPIST-1d, E, F, and G. And then there's another system called LHS 1140, specifically the planet LHS 1140b. Why are these the absolute top-tier targets?
The TRAPPIST-1 system is nothing short of an astrophysical marvel. It is located about 40 light years away from Earth.
Which sounds incredibly far.
Well, yes, 40 light years is an unimaginably vast distance for human travel. It would take our fastest current probes hundreds of thousands of years to get there.
Right.
But in galactic terms, it is literally right down the street. It is a single, ultra-cool red dwarf star, only slightly larger than the planet Jupiter, but it has a whole family of 7 rocky, Earth-sized planets crammed in tight around it.
7 Earth-sized planets around one star.
Yes. And the entire planetary system could fit comfortably inside the orbit of Mercury in our own solar system.
Wait, really? The whole system?
The whole thing. They are packed incredibly close together, and at least 4 of them, D, E, F, and G, sit squarely within that 3D habitable real estate we just talked about.
Okay, I have to stop you because this is where the sheer logistics of this blow my mind.
It's hard to wrap your head around.
You are talking about a star that is 40 light years away, which is roughly, 235 trillion miles?
Roughly, yes.
You're telling me there are 7 rocks orbiting it. And we know their mass, we know they are rocky, and we know exactly how much light they are receiving. But we cannot actually see them.
We cannot.
We don't have a high-resolution photograph of TRAPPIST-1. To our best telescopes, the star itself is barely a pixel of light. The planets are completely invisible.
That's entirely correct.
So how do we actually know any of this is true? How do we have this level of detail?
It is a testament to the ingenuity of modern astrophysics. We do not need to resolve a direct image of the planet to know it's there or to measure its physical properties.
Okay, how does that work?
Astronomers rely on 2 brilliant indirect methods of observation. The first, and the one responsible for the vast majority of our exoplanet discoveries, is the transit method.
This is essentially watching for planetary shadow, right?
Exactly. Imagine you are staring at an intense searchlight from 10 miles away. Now imagine a moth flies exactly between you and the center of that searchlight.
You wouldn't be able to see the moth.
The moth is far too small for your eye to resolve at that distance. But for a tiny fraction of a second, the moth blocks a microscopic percentage of the searchlight's beam.
So the light gets a tiny bit dimmer.
Yes. The overall brightness of the light hitting your eye dips just a tiny bit. We do the exact same thing with telescopes.
We just stare at the star.
We stare at a star and measure its total light output with incredibly sensitive light meters called photometers. If a planet's orbit happens to cross right in front of the star from our perspective on Earth, we see a tiny dip in the star's brightness.
And the characteristics of that dip tell us a massive amount of information. Like if we see the dip happen exactly every 12 days, we know the planet's year is 12 days long.
Yes, that gives us the orbital period. And the depth of the transit, the exact percentage of light blocked, tells us the fizzle diameter of the planet.
Because a bigger planet blocks more light.
Exactly. If it blocks a larger percentage, it's a gas giant like Jupiter. If it blocks a tiny sliver, it's a small, rocky planet like Earth.
That is so elegant.
It really is. By mapping the exact shape of the light curve, how quickly the starlight dims as the planet begins its crossing, and how it brightens as it exits, we can even deduce orbital details.
Which planets on our list were found this way?
The transiting planets on our VIP list that receive Earth-like light include TRAPPIST-1e, TOI-715b, Kepler 1652b, Kepler 442b, and Kepler 1544b.
But the transit method has a huge geographical blind spot, doesn't it?
Oh, massive.
It only works if the planetary system is perfectly edge-on to our line of sight from Earth. If the planet orbits, like, above or below the star, from our perspective.
It never crosses the face of the star from our point of view.
So it never casts a shadow toward Earth, and the transit method sees absolutely nothing.
And that is exactly why the second technique is so vital. The radial velocity method, more commonly known as the wobble method.
The wobble method, I love that name.
It's very descriptive. This technique relies entirely on gravity. We are taught in school that planets orbit stars, with the star sitting perfectly stationary in the center. But Isaac Newton taught us that gravity is a mutual attraction. The star pulls on the planet, keeping it in orbit, but the planet's mass also exerts a tiny, continuous gravitational tug back on the star.
Right, so if an adult is spinning around in a circle, holding the small child by the hands, the child is doing a big orbit.
Yes.
But the adult in the center isn't perfectly still. The weight of the child pulls the adult slightly off-center, making them wobble in a tiny circle as they spin.
That is exactly what happens to the star. As the unseen planet orbits, it pulls the star in a tiny circle. From Earth, we see the star being pulled slightly toward us, then slightly away from us.
But we can't see the wobble directly, can we?
No, the movement is far too small. But we measure this motion using the Doppler effect.
Like when a police siren changes pitch as it drives past you.
Precisely. When the star is pulled slightly toward Earth, the light waves it emits get slightly compressed, shifting toward the blue end of the color spectrum. When the star is pulled away from us, the light waves stretch out, shifting toward the red end of the spectrum.
So the star is basically changing color slightly.
Yes. By analyzing the starlight with spectrometers, we can detect this incredibly subtle red-blue color shift over time.
But wait, how does that work for a system like TRAPPIST-1 where there are 7 planets?
That's where it gets complicated.
Right. If you have 7 different children of different weights, pulling on that adult at different speeds and different angles, that wobble isn't going to be a clean, simple circle.
No, not at all.
It's going to be an incredibly chaotic, messy jerk. How do scientists untangle the Doppler shift of a star being pulled in 7 different directions at once?
That is where the mathematics become truly beautiful. You are correct. The resulting signal is a complex, overlapping mess of wave frequencies.
So how do they sort it out?
Astronomers use mathematical tools like Fourier transforms to take that highly complex, messy wave and decompose it into its individual, simple sine waves.
It's like unbaking a cake.
Exactly. It's the mathematical equivalent of listening to a full symphony orchestra playing a chord and using a computer program to isolate and identify the exact note being played by the oboe, the cello, and the flute individually.
That is incredible.
By isolating each frequency of the wobble, we can determine the exact mass and orbital period of every single unseen planet tugging on that star.
And which ones did we find this way?
The planets on our list found this way include Proxima Centauri b, Wolf 1069b, and the planets in the GJ 1061 and GJ 1002 systems.
So between the transit shadow and the radial velocity wobble, we can piece together the size, the mass, the density, the orbit, and the exact amount of stellar energy hitting these 45 rocks.
You can paint a very detailed picture without ever actually seeing the planet.
But there is a massive caveat to all of this excitement that we have to address. Just because a planet is the right size and sitting at the right distance does not mean it is an alien paradise.
No, the habitable zone is just a prerequisite.
Right. It is entirely dependent on one fragile feature.
Yes. The elephant in the room of astrobiology. The planet must be able to hold on to a robust atmosphere.
Because without an atmosphere...
Without atmospheric pressure, the habitable zone means absolutely nothing.
We have a perfect example of this right next door. If you take a perfectly rocky body and put it at the exact distance Earth is from the sun, but it lacks an atmosphere, you get a moon.
Exactly. The moon is technically in the habitable zone.
It receives the exact same average solar energy as Earth, but the moon's surface is a nightmare.
It is.
In direct sunlight, the temperature skyrockets to over 250 degrees Fahrenheit.
And in the shadows.
In the shadows, it plunges to minus 200 degrees.
Huge swings.
If you poured a glass of liquid water on the surface of the moon, it would violently boil into vapor due to the lack of pressure, and then immediately freeze into ice crystals before sublimating off into the vacuum of space.
Precisely. An atmosphere acts as a planetary blanket. It distributes heat around the globe, smoothing out those extreme temperature swings between day and night.
And it provides the barometric pressure required to keep water in a liquid state.
Yes, and holding onto an atmosphere is incredibly difficult, especially for planets orbiting red dwarfs.
Because they're so close to the star.
Well, we mentioned earlier that red dwarfs are dim, but they are also notoriously volatile, especially in their youth.
What do you mean by volatile?
They frequently unleash massive stellar flares and coronal mass ejections. These are basically hurricanes of high-energy charged particles.
So if a planet is huddled right up close to the star in the habitable zone, it is taking the full brunt of those solar storms.
Right to the face.
If the planet doesn't have a strong magnetic field to deflect that radiation, those solar winds could physically strip the atmosphere away into space over 1 billion years, leaving a barren rock.
Which is exactly why being on the list of 45 is just surviving the first round of cuts.
The universe is incredibly chaotic, and some of these planets are not sitting comfortably in the middle of the zone. They are fighting for their lives right on the absolute edge.
And that leads to one of the most fascinating aspects of how scientists are studying this catalog. They're not just looking at the safe, comfortable planets.
Right.
Researchers are deeply focused on pushing the limits, using our own solar system's failures as the ultimate reference guide for planetary death.
Because when we look at our cosmic neighborhood, we have 3 rocky planets clustered near the habitable zone: Venus, Earth, and Mars.
Right. Earth is the gold standard of habitability. Venus and Mars are the ultimate cautionary tales.
And they are both dead for completely opposite reasons. Let's talk about Venus. Venus is the nightmare scenario of flying too close to the sun.
It really is.
It's just a little bit closer to our sun than Earth is, receiving slightly more stellar energy.
Yes. Venus suffered a runaway greenhouse effect. Early in its history, it may have actually had oceans.
Really? Like liquid water oceans?
It's very possible. But as the sun gradually brightened over billions of years, Venus got too warm.
So the oceans just evaporated.
Yes, filling the atmosphere with massive amounts of water vapor.
And we talked about how water vapor is a potent greenhouse gas.
Far more effective at trapping heat than carbon dioxide. So this trapped more heat, which baked actual carbon dioxide out of the surface rocks, thickening the atmosphere even further in this unstoppable feedback loop.
A runaway train.
Exactly. Today, the atmosphere of Venus is 90 times denser than Earth's, composed almost entirely of carbon dioxide with clouds of sulfuric acid.
Which is terrifying.
And the surface temperature is over 860 degrees Fahrenheit, hot enough to melt lead. It is a literal hellscape.
And then you have Mars, which is the tragedy of losing the blanket entirely. Mars is further out, on the colder edge of the habitable zone.
But distance wasn't Mars's primary downfall, it was size.
Because it's a lot smaller than Earth.
Mars is significantly smaller. Because it is smaller, its internal geological core cooled down much faster.
Oh, right.
On Earth, the swirling molten iron in our outer core generates our global magnetic field, our magnetosphere.
Which acts like a shield.
Exactly. When Mars's core cooled and solidified, its magnetic dynamo shut down.
It lost its shield.
Without a magnetic shield to deflect the intense solar wind blasting out from the sun, that stream of charged particles collided directly with the Martian upper atmosphere.
Just stripping it away.
Molecule by molecule, over millions of years, the solar wind relentlessly eroded the atmosphere.
So with only a thin, wispy atmosphere left, Mars couldn't hold on to any heat or provide enough pressure for liquid water.
And it froze into the barren, irradiated desert we see today.
So when researchers are analyzing these 45 exoplanets, they are actively looking for the Venus and Mars analogs.
They absolutely are.
They are specifically targeting planets that receive stellar energy right on the ragged edges of the habitable zone to test if our mathematical models of planetary death are actually correct.
Exactly. They are stress testing the physics.
So who's on the edge?
On the inner hot edge, the Venus boundary, they are scrutinizing transiting planets like K2-239d, TOI-715, and K2-3d, alongside wobbling planets like Wolf-61c.
These are the ones getting baked.
Right. These are planets receiving the absolute maximum amount of energy a world can theoretically take before it suffers a Venus-style runaway greenhouse catastrophe.
Yet on the other side,
Conversely, on the outer freezing edge, the Mars boundary, they are observing planets like TRAPPIST-1e, Kepler-441b, and GJ-102.
so they are freezing.
These worlds receive so little starlight that they are teetering on the brink of global glaciation, freezing over completely into snowball planets.
Okay, but we are still assuming these planets stay in their designated lanes.
Which they don't always do.
Here is a wild variable that completely throws a wrench into the whole Goldilocks concept.
Yeah.
What if the planet's orbit isn't a perfect circle?
Orbital eccentricity.
We always picture planetary orbits like a record spinning smoothly on a turntable. But gravity is messy, and planetary orbits are often elliptical or oval-shaped.
Very often.
And a highly eccentric planet doesn't just sit in the habitable zone, it physically travels in and out of it.
Orbital eccentricity is perhaps the most dynamic and challenging factor in assessing long-term habitability. It fundamentally challenges the idea of a stable climate.
Imagine holding your breath while swimming underwater. That is what these planets are doing.
That's a great way to think about it.
For part of its year, an eccentric planet's oval-shaped path swings it way out into the deep freeze, far beyond the outer edge of the habitable zone.
The oceans freeze solid.
The atmosphere might even become so cold that gases like carbon dioxide literally snow out of the sky and collapse onto the surface.
Total deep freeze.
Then, a few months later, the orbit whips the planet back inward, hurtling it right through the habitable zone and incredibly close to the star.
The massive ice sheets violently melt.
The oceans boil. Huge continent-spanning hurricane systems ravage the surface as the atmosphere rapidly expands.
Sheer chaos.
Exactly. How long can a planet dive into the freezing or boiling zones and still maintain any semblance of a habitable environment when it crosses back into the safe zone?
That is precisely the mystery astronomers are trying to resolve by studying these edge cases. It really comes down to a concept called thermal inertia.
Thermal inertia, what is that?
If a planet has deep, massive oceans, water takes a very long time to heat up and a very long time to cool down.
Right. It's why coastal cities have milder weather than inland areas.
Exactly. A massive ocean could act as a thermal battery. If the planet dips out into the freezing zone for a few weeks, the surface of the ocean might freeze, creating a layer of ice that actually insulates the liquid water deep below, preserving the heat.
Like a frozen lake in winter. The fish are still swimming around underneath.
Precisely. So life could survive deep underwater even while the surface goes through a deep freeze.
Okay, what about when it swings in close to the star?
Even if the surface environment is subjected to extreme boiling and freezing cycles, we know from studying Earth that biology is astonishingly resilient.
Life finds a way.
It does. We have extremophiles on our own planet organisms, like tardigrades or certain strains of archaea found in hydrothermal vents or deep Antarctic ice that can survive immense radiation, extreme heat, deep freezes, and even the vacuum of space.
Those water bears are indestructible.
They really are. So by observing these highly eccentric exoplanets, we aren't just looking for ideal Earth-like conditions. We're asking a profound biological question.
How much chaos can a planetary climate tolerate before habitability is irreparably lost?
Exactly.
So we have the map. We understand the thermodynamic recipes. We have the 35 prime candidates, the 24 conservative 3D bets, and we know exactly which worlds are testing the absolute limits of physics with eccentric orbits.
We know exactly where to point the telescopes.
But knowing the cosmic address doesn't mean you can read the mail.
That is very true.
How do we actually plan to look at something that is 48 light years away and conclusively say, ah, yes, there is water vapor there, or look, there are biosignature gases like oxygen and methane, because finding the dot of the planet was just the first hurdle.
Identifying the coordinates was a monumental generational achievement, but it is only the targeting system.
Right. Now we need the hardware.
To actually study these 45 planets, to probe their alien atmospheres for the chemical fingerprints of life, we need an unprecedented leap in hardware. We need the next generation of cosmic eyes.
And the timeline of human ingenuity here is just staggering. We are currently living in a golden age of astronomy, but the technological roadmap for the next 2 decades reads like science fiction made real.
It really does. It is a massive coordinated mobilization of global scientific capability.
Let's break down the arsenal of monumental observatories that are going to use this exact catalog of 45 planets as their primary targeting list over the coming years.
Well, right now, operating actively as we speak, we have the James Webb Space Telescope, or JWST.
Which has already been sending back mind-blowing images.
It is currently the most powerful space observatory ever built. It is specifically optimized to see in the infrared spectrum of light.
Which, as we discussed earlier, makes it incredibly adept at peering into the atmospheres of planets orbiting those dim red dwarf stars.
Exactly. It's perfectly tuned for these red dwarf systems. But JWST is just the vanguard of this effort.
Right, because looking ahead, the cavalry is coming.
It is. In 2027, we expect the launch of the Nancy Grace Roman Space Telescope.
The Roman telescope? What's special about that one?
The Roman telescope is designed with a field of view 100 times greater than the Hubble Space Telescope.
Wow, 100 times.
Yes. While it will survey massive swaths of the sky and discover thousands of new exoplanets, its real power lies in providing crucial, wide-field contextual data for the systems we are already targeting.
So it's looking at the big picture. And then in 2029, we aren't just relying on instruments in space. We are building absolute giants on the ground.
Yes, the Extremely Large Telescope, or ELT, which is such a straightforward name. I love it.
Astronomers are great at naming things. The ELT is currently under construction high in the Atacama Desert in Chile.
Why there?
High altitude, incredibly dry, very little atmospheric distortion. When completed, it will be the largest optical and near-infrared telescope in the world.
How big is it?
Its main segmented mirror will be over 39 meters across, roughly half the length of an American football field.
A mere half the size of a football field. That's insane.
It will utilize advanced adaptive optics, which use lasers to measure atmospheric distortion and physically deform the telescope's mirrors thousands of times a second to cancel out the blur of Earth's atmosphere.
So it basically untwinkles the stars.
That's exactly what it does. The light-gathering power of the ELT will be so immense that it might actually be able to achieve direct imaging of some of the larger rocky planets in the habitable zones of nearby stars.
Direct imaging. Meaning we aren't just inferring the planet exists because of a shadow or a wobble.
No, we actually capture a distinct pixel of light representing the planet itself, separate from its star.
That is wild.
Yeah.
But the true holy grails of exoplanet science are coming even later, right?
Looking toward the 2040s, NASA is developing the Habitable Worlds Observatory.
The HWO.
This is a mission explicitly designed from the ground up for one primary, singular purpose: to directly image Earth-sized planets around sun-like stars and meticulously analyze their atmospheres for chemical signatures of life.
How is it going to manage that with sun-like stars being so bright?
It will utilize advanced next-generation coronagraphs.
A coronagraph is essentially a physical disk inside the telescope that perfectly blocks the blinding glare of the host star, revealing the faint planets orbiting around it, right?
Exactly.
Kind of like putting your thumb up to block the sun so you can see a bird flying nearby.
A perfect analogy. But engineering a coronagraph that can suppress starlight by a factor of 10 billion to 1, which is required to see an Earth-like planet next to a sun-like star, is an engineering challenge of historic proportions.
10 billion to 1? Yeah, that's not easy.
And looking even further into the future, there is the proposed Large Interferometer for Exoplanets, or the LIFE project.
Okay, what is life?
This concept would involve a flotilla of individual space telescopes flying in ultra-precise formation.
Like a swarm.
Yes. By combining the light captured by all the individual telescopes through a process called interferometry, they act as one colossal virtual observatory. capable of unprecedented resolution.
So we have this incredible roadmap of machines, but let's bring it back to the targets right now today.
Okay.
Here is where the mechanics of astronomical observation get really fascinating. We talked earlier about researchers utilizing JWST right now and how observation programs are focusing heavily on the TRAPPIST-1 system and TOI-715b.
Yes, those are prime targets.
I have to push you on this. Out of the 45 planets on this painstakingly curated list, why are astronomers throwing so much precious, highly competitive JWST telescope time, specifically at TRAPPIST-1 and TOI-715b? What makes them the absolute priority?
It comes down to a matter of mathematical advantage and a concept in observational astronomy known as the contrast ratio.
A contrast ratio.
Yes. The technique JWST uses to study atmospheres is called transmission spectroscopy.
Okay, how does that work?
When a planet transits in front of its star, a tiny fraction of the starlight actually passes through the very edges of the planet's atmosphere before continuing on its journey to Earth.
And as that starlight passes through the alien atmosphere, the different gases in that atmosphere, water vapor, carbon dioxide, methane absorb specific, distinct wavelengths of light.
Precisely. They leave dark gaps or chemical fingerprints in the spectrum of light that reaches our telescope.
So we can look at the gaps and say, that's oxygen.
Exactly. But capturing that signal is incredibly difficult.
Why?
Let's say you want to study an Earth-sized planet orbiting a star exactly like our sun. The sun is massive, and it is blindingly bright.
Right.
An Earth-sized planet next to it is microscopic, and its atmosphere is a razor-thin sliver. The difference in brightness, the contrast ratio, is roughly 10 billion to 1.
So the star just overpowers everything.
It is the equivalent of trying to spot a single glowing firefly hovering exactly 1 millimeter away from the lens of a massive coastal lighthouse searchlight from 50 miles away.
That is impossible.
The brilliant glare of the star completely washes out the incredibly faint, delicate atmospheric signal filtering through the planet's atmosphere.
But TRAPPIST-1 and TOI-715b offer a massive mechanical advantage because they are different types of stars.
Radically different. They're small, ultra-cool red dwarfs.
Like we talked about before.
TRAPPIST-1 is barely larger than the planet Jupiter. It is thousands of times dimmer than our sun. Because the star is so small, the contrast ratio is far, far more favorable.
So the firefly isn't competing with a lighthouse anymore.
Furthermore, because the star is dim, the habitable zone is much closer in. The planets are practically right on top of the star. When TRAPPIST-1 transits across the face of its tiny star, it doesn't just block a microscopic fraction of light. The physical disk of the planet blocks a highly measurable, significant percentage of the star's total surface area.
Because the star is small, the planet casts a relatively huge shadow, and the rim of atmosphere we are trying to look through is proportionally much larger compared to the star behind it.
Exactly. The starlight filtering through the planet's atmosphere on its way to Earth carries a much stronger, clearer, thicker signal.
So it's just easier to read.
Against a massive, blinding star, detecting that atmospheric transmission spectrum is nearly impossible with current technology. But against a small, dim red dwarf, the atmospheric signature of these little rocky planets is much, much easier to isolate and analyze.
They are the absolute low-hanging fruit of the cosmos for atmospheric characterization.
They really are.
And this isn't just theoretical planning for a mission in 2040. This is happening tonight.
It is happening right now. Researchers are actively using this exact catalog to take early foundational looks at 10 specific planets from the list that receive radiation very similar to Earth.
And they are focusing on those red dwarfs.
They have explicitly identified TRAPPIST-1 and TOI-715b as immediate, high-priority targets that are close enough and orbit favorable enough stars to be studied intensely with JWST.
This catalog of 45 planets is not a theoretical wish list filed away in an academic drawer. It is an active, operational treasure map being utilized this very second by the most powerful observatory humanity has ever constructed.
It's a very exciting time to be an astronomer.
So let's pull all of this together. Think about the monumental intellectual journey we just traced.
It's been quite a ride.
We started out staring up at a chaotic, overwhelming night sky filled with 6,000 confirmed exoplanets. A haystack of literal cosmic proportions.
And through rigorous astrometry and thermodynamic analysis, that haystack was filtered down to 45 prime rocky candidates residing in the habitable zone.
It was narrowed even further to 24 conservative bets that survived the grueling tests of 3D global climate modeling.
We explored the edge cases, the extreme planets dipping in and out of the freezing and boiling zones, pushing the absolute limits of biological survival.
And we mapped out an armada of current and future space telescopes that are actively pointing their lenses at these 45 exact coordinates to search for the chemical breath of alien life.
And this brings us to the ultimate profound realization of this entire endeavor.
What's that?
The true value of this catalog extends far beyond just the sheer thrill of discovering extraterrestrial biology.
Okay, how so?
Yes, we want to know if there is a Rocky out there, or alien extremophiles, or entire biospheres glowing in neon biofluorescence under a red sun. But more deeply than that, this catalog is a mirror held up to our own world.
By studying them, we study ourselves.
Exactly. When we use these telescopes to study the planets that failed, when we observe the Venus and Mars equivalents scattered across the galaxy, we learn about the terrifyingly precarious nature of our own existence.
Because we see what can happen.
We learn exactly how much solar energy, how much atmospheric pressure, how much orbital stability is required to keep a planet breathing. We tend to view Earth as a permanently guaranteed paradise.
We take it for granted.
We do. But it is not guaranteed. It is a complex, dynamic, and fragile system that has undergone massive, catastrophic climatic shifts in its past.
We've had snowball Earth phases, and we've had hothouse Earth phases. The balance is incredibly delicate.
And by actively observing the physical failures and the successes among these 45 alien worlds, we build a far more comprehensive physical understanding of planetary evolution.
It's like having more case studies for disease.
Exactly. We learn exactly what mechanical processes cause a world to die, which inherently teaches us how to better protect and understand the only world we know that is currently alive.
It is a sobering, beautiful, and incredibly vital perspective.
I think so too.
Which leaves me with a final lingering thought for you to ponder long after you finish listening today.
Let's hear it.
Imagine the day, maybe just a few short years from now, when astronomers point the James Webb Space Telescope or the upcoming ELT at one of those extreme, hot edge case planets. Let's say K2-239d, a planet roasting on the inner boundary of habitability. They analyze the transmission spectrum of its atmosphere, the data downloads to Earth, and it reveals undeniable chemical signatures suggesting that the planet used to be exactly like Earth.
Oh, wow.
It shows the ghost of a destroyed water cycle, the isotopic ratios of a vanished moderate climate, a stable atmosphere, right up until the moment it tipped over the edge, suffered a runaway greenhouse effect, and boiled alive.
The remnants of a dead world.
If we find the chemical, fossilized remains of a dead Earth out there in the stars, what does that tell us about the ultimate ticking clock on our own perfect, fragile blue world?
That's a chilling thought.
If you wake up from a deep sleep like the astronaut in Project Hail Mary, the scariest thing might not be finding out you are unimaginably far from home. The scariest thing might be looking through the telescope and realizing just how easily home can disappear.